The light hits you before anything else does. Not warmth, not radiation. Light, a wall of it, red and swollen and wrong, filling your entire field of vision the way nothing in nature is supposed to fill it. This is not the sun you know. The sun you know is a white-yellow point in a blue sky, something you were told never to look at directly, something that fits inside the gap between your thumb and forefinger when you hold your arm out. This thing doesn't fit anywhere. It has expanded beyond the geometry of something that should exist. It is 200 times wider than it used to be. It has already swallowed Mercury. It has already swallowed Venus. And the outer edge of it, the bloated, convulsing, slow-motion catastrophe of its surface, is close enough that you can watch it move. A star is dying in front of you. You are close enough to feel it happen. You will not survive the next few minutes, but the way you don't survive them is more horrifying than anything the word death was designed to contain. Red giants are the most visually magnificent objects in the night sky. Betelgeuse, the bright red star at Orion's shoulder, visible on any clear winter night from anywhere on Earth, is one of the most photographed, most studied, most beloved stars in human astronomical history. Ancient cultures built mythologies around it. Modern astronomers have measured it with instruments capable of resolving its actual disk, something almost no other star allows. It glows with a deep, saturated red that feels warmer than the cold blue-white of younger stars. If it replaced our sun, its surface would extend past Jupiter's orbit. It is a giant in the most literal sense, vast, warm, ancient, burning the last of what it has left. In late 2019, Betelgeuse dimmed dramatically. By early 2020, it had faded to roughly 40% of its normal brightness. Astronomers worldwide pointed every available instrument at it. The question in every observatory, in every paper, in every conference, call between stunned researchers was the same. Is this it? Is it about to go? It wasn't. Not yet. A massive surface eruption had ejected material that temporarily obscured the star, but the episode revealed something important. Betelgeuse is not stable. It is not the eternal, fixed, reliable point of light that the word star implies. It is a volatile, convulsing, pressurized system in the final chapter of its existence, burning through its last fuel at a rate that makes the end not a distant abstraction, but a genuine event on an astronomical timescale. It will explode as a supernova, visible from Earth in daylight, brighter than the full moon, sometime in the next 100,000 years. In cosmic time, that is now. But standing inside one is different from watching one from light years away. And the difference is not one of degree, it is one of category. The surface of a red giant runs between 3,000 and 4,000 degrees Celsius. This sounds less extreme than the sun's surface at $5,500 degrees, and that comparison is almost comically misleading, because the relevant number is not the temperature at the surface, but the total energy output, and a red giant with a surface area potentially 1 billion times larger than our sun's radiates more total energy than you can process as a concept. At the distance, your body could theoretically approach before structural failure, the radiant heat alone. Not plasma contact, not particle bombardment, just the infrared energy radiating from the surface would raise the temperature of your suit's exterior to thousands of degrees in seconds. The suit vaporizes, not melts, not chars, vaporizes. The material transitioning directly from solid to gas faster than the word burns has time to apply. The thermal energy then reaches your body, which is approximately 37 degrees Celsius and 60% water, and the encounter between those two realities takes less time than a single nerve impulse. You do not feel it. This is not comfort. It is just physics. The process happens faster than pain signals travel. But here's the problem. Getting close enough for any of that to happen requires surviving the outer layers first. And the outer layers have their own agenda. A dying star bleeds, not metaphorically. Red giants shed mass continuously through stellar winds, streams of charged particles and plasma ejected from the surface at hundreds of kilometers per second. Our sun loses mass through solar wind too, but modestly, roughly 1 million tons per second, a trivial fraction of its total mass over its lifetime. A red giant like Betelgeuse loses mass at a rate estimated to be tens of millions of times greater than our sun. It is actively dissolving into space, shedding its outer layers in a continuous, violent exhalation that extends for light years beyond the visible surface. Flying through that wind is not like flying through weather. It is like flying through the interior of a particle accelerator, pointed directly at you. The charged particles hit your ship, in the theoretical scenario where you have one, where something exists between you and the star, and they don't just heat the surface, they penetrate. High-energy particles punch through shielding, through metal, through the biological tissue of anyone inside, stripping electrons from atoms, severing molecular bonds, depositing radiation damage in every cell simultaneously. The Apollo astronauts on their way to the moon were exposed to enough cosmic radiation that some of them reported seeing light flashes behind closed eyes, particles passing directly through their eyeballs and interacting with the optic nerves. That was in the relatively protected environment of the inner solar system, during periods of low solar activity. Inside a red giant's stellar wind, the particle flux would be billions of times more intense. The radiation dose that kills a human being is measured in grays. The stellar wind of a dying star would deliver thousands of grays per second. But it gets worse. The visible edge of a star is not a surface. Not in any sense that the word surface implies. There's no boundary to cross, no point where gas becomes solid, no moment of contact, the way contact works with any object you have ever touched. The photosphere, the layer we see as the star's edge, is the depth at which the gas becomes opaque to visible light. Below it, the plasma is so dense that light cannot travel in a straight line. But it is still gas. Still plasma. Still an extraordinarily hot, pressurized, ionized fluid extending inward for hundreds of millions of kilometers before reaching anything approaching a distinct interior region. You do not enter a dying star. You become progressively more inside it. The transition is gradual and total, and every meter of depth adds temperature and pressure and density in a progression that has no plateau, no safe zone, no depth at which conditions stabilize into something survivable. The pressure at the base of a red giant's outer envelope crushes with a force that makes Jupiter's interior, already a place where hydrogen becomes liquid metal, seem gentle. At sufficient depth, the plasma is so dense that atoms cannot retain their electrons. They are stripped bare, nuclei floating in a sea of free electrons, a state of matter called a degenerate plasma, governed by quantum mechanics rather than conventional thermodynamics. This is not an environment that has analogs in human experience. It is not hot water or high pressure or strong wind scaled up. It is a different phase of matter operating by different rules. In the human body, which is held together by exactly the electron bonds that no longer exist at this depth, simply ceases to be an organized system. And this is where things change. At the center of a dying red giant, something is ending. A star lives by fusion, hydrogen nuclei colliding and merging into helium, releasing the energy that makes the star shine, generating the bagwoods, outward pressure that counteracts gravity and keeps the star from collapsing under its own weight. Our sun has been doing this for 4.6 billion years. It has approximately 5 billion years left. But a dying star, a star that has become a red giant, has exhausted the hydrogen in its core. The fusion has migrated to a shell around the core, burning outward while the core itself sits inert, composed entirely of helium, growing denser and hotter as more helium is deposited on it from the fusion. Shell above. The helium core heats toward a threshold. When it reaches approximately 100 million degrees Celsius, nearly 20 times the temperature required to ignite hydrogen fusion, something called the helium flash occurs. In stars of certain masses, this ignition is not gradual. It is explosive. The entire helium core ignites simultaneously in a runaway fusion event, releasing, in a matter of seconds, more energy than the star has radiated over the previous million years. This energy does not reach the surface visibly. It is absorbed by the outer layers, but the structural shock propagates outward through the stellar interior like a pressure wave through an ocean. From inside the star, when this happens, the shock wave does not feel like an explosion in any familiar sense. There is no sound in plasma. There is no visible shock wave front. There is simply a sudden, violent increase in pressure from every direction simultaneously. A compression event that supersedes every other. Ongoing process, and resets the physics of the interior in a moment. But that's not even the worst part. Stars between roughly 8 and 20 times the mass of our sun do not end as red giants peacefully shedding their outer layers. They end as supernovae. The core collapses. In less than a second, in fractions of a second, the iron core at the center of a massive dying star reaches the density of an atomic nucleus and stops collapsing with a violence that sends a shockwave back outward through the infalling stellar material. The result is an explosion releasing more energy in 10 seconds than our sun will emit in its entire 10 billion year lifetime. The Crab Nebula, that beautiful feathery cloud of glowing gas visible through small telescopes in the constellation Taurus, is what a supernova leaves behind. Chinese astronomers recorded the explosion that created it in 1054 AD. They wrote that the new star was visible in daylight for 23 days. What remains at the center of that nebula is a pulsar, a neutron star 20 kilometers wide, spinning 30 times per second, radiating beams of electromagnetic energy with the regularity of a cosmic clock, the entire mass of a star, compressed to the size of a city. If you are inside the star when this process begins, the sequence of events between the core collapse and the shockwave's arrival at your position takes seconds. The neutrino burst, a flood of nearly massless particles produced in the collapse, so numerous that even the extremely low probability of neutrino interaction becomes relevant, passes through you like a ghost, depositing enough energy in that passage to kill you before the shockwave arrives. You are killed by particles that almost never interact with anything, because almost never, multiplied by the number of neutrinos in a collapsing stellar core, becomes certainty. The universe uses its most elusive particles to make sure nothing survives. There is iron in your blood right now, not metaphorically, actual. Iron atoms, incorporated into hemoglobin molecules, carrying oxygen through your cardiovascular system, keeping you conscious and alive as you watch this video. That iron was not made on Earth. It was not made in the sun. The sun is not hot enough, not massive enough, not old enough to have fused iron in its core. The iron in your blood was forged inside a star that died before our solar system existed, a star that ran its full life cycle, fused lighter elements into heavier ones all the way up to iron, and then exploded, scattering those elements into the galaxy. The cloud of gas and dust that eventually became our solar system incorporated that explosion's debris. The Earth formed from it, life formed from it, you formed from it. You are, in the most literal physical sense, the recycled remnants of a dying star. The iron in your blood, the calcium in your bones, the oxygen you are breathing, none of it was created on Earth. All of it was forged in stellar cores and dispersed by stellar deaths across billions of years and billions of light years before eventually arriving here, assembled by chemistry into the temporary, fragile, remarkably complex arrangement that is currently watching a video about the place it came from. We talk about dying stars as threats, as cosmic dangers, as environments categorically hostile to life. All of that is true. But it is also true that without dying stars, there is no life to threaten. The explosions that would destroy you are the same. Explosions that built you. The stellar winds that would strip your molecules apart are the mechanism by which the galaxy distributes the materials that molecules are made from. The core collapse that generates a lethal neutrino burst also synthesizes, in that brief, violent moment, the heavy elements that the universe could not have made any other way. You cannot survive inside a dying star, but you could not exist without one. The universe built you out of its most violent processes, and then made those processes lethal to you. It is the deepest irony in all of physics, that the events capable of ending you in seconds are the same events that produced every atom that makes you something that can be ended. Stars do not die for us. They never knew we existed. But we are here because they died, burning through their fuel across billions of years, seeding the void with the materials of everything that would come after, in different architects of a universe they would never see completed. You are what a dying star left behind. And somewhere out there, another one is ending right now, building the materials for something that doesn't exist yet. The universe wastes nothing, not even its own destruction.